Hi, in this video, we're going to look at normality, that is normal distribution for composition data. Now, composition data is data that we have non-negative values, so 0 or positive, usually positive, and they add up to a constant value. So for example, if I wanted the fraction for each observation relative to each other within one particular observation, then I would have it add up to 1 as my composition values. Or maybe I want percentages, and where each measurement is the percentage of a particular field within the observation. There, we would have things add up to 100. I could also have 1,000,000 for parts per million. So composition data is very different than regular data that we talk about in statistics. So one thing that's a major impact of this, imagine that I have composition data. So for each observation, I have multiple fields that are being measured, and all of the values add up to 1 or 100, 1,000,000, whatever you want to pick. I prefer 1 because it's just mathematically more convenient. All right, so if you think about that for a moment, if one value goes up, then somewhere the other values have to go down, one or more other measurements have to decrease to make sure that things work out to be exactly 1 or 100, 1,000,000, whatever value we have for the summation. All right, so that fundamentally creates a different relationship between our variables. We have, in fact, if I only have 2 fields in a composition, well, as one goes up, the other goes down, we have to have a perfect -1 correlation between them when I have exactly 2. So in general, when we have composition data, we expect to see negative correlations between our measurements just because we have this restriction. All right, so if we think for a moment, well, what about this whole normality business? Normality is a very different structure than what composition data gives us. And because of that, we're not going to have normal, most of the time, we're not going to have normal composition distributed data. What we're going to have instead is that I'm going to go, hey, let's do a log transform on my composition data. And then, so a log ratio transform. And then if I have normal, then I'm going to use that as normally distributed, do my analysis on the log ratio transform data, use normal distribution for my analysis. Then after I get my results, convert back to the original version. All right, so the information that we're going to be going over is from Geostatistics for Composition Data with R, Chapter 3. Here are the names of the authors. Students at the University of Central Florida can download the textbook for free through Springer link by going to the library's website. Here is the package in R that the textbook leans on very heavily. Also, the package compositions is used quite a bit. Here is one of the author's professional websites, and here is the crayon page for compositions. All right, so let's get down to it. All right, so we want to talk about log ratio transform data that is normally distributed. And so the big idea here is that I have composition data and I want to have it. So under assumption, more than likely it's going to be by assumption, we're going to have that our log ratio transform data is normally distributed or approximately normally distributed. And then I'm going to do my analysis under that assumption, and then I'm going to convert back to compositions. Okay, so normal distribution is all over the place in statistics. Why is that? Really because of the central limit theorem. Central limit theorem says that if I'm taking averages and I'm consistent with sample size, then under mild assumptions, the distribution of the average is going to converge to normally distributed. And so this gives us a way of making inference on our data without having to have additional specific narrow nuance hypotheses and assumptions going on. It works out that with the central limit theorem, we really can, most of the time, work around in slick ways to be able to use normal distribution to solve our problems, as long as my sample size is decent. All right, so I can't, because of the structure of composition data, that restriction that we have between 0 and 1, it's not feasible to just go directly at normal. Instead, we're going to incorporate log ratio transforms, and even then, there's still some stickiness to it. So to incorporate the normal distribution for compositions, we're going to use HSN Mahalanobis distance between two compositions. All right, so this is going to be a distance metric between two composition observations. And so here I've got two distinct composition observations. They both have their vectors, they have non-negative entries, and their entries add up to 100, 1 million, whatever is right for my project. Now you'll notice also we have the distance squared here. So technically the distance needs to be square rooted, but for what we're going to do in a moment, we're going to be having a square on there. So the authors chose to leave it as is. Okay, so what we're going to do, whatever transformation we're going to pick, we're going to write that in the format of the generalized log ratio transform presentation. So GLR on each of these, take the difference, all right, and take the same value here. And you'll notice I've got transpose on the left, and I've got the regular vector straight on the right. And then in the middle, I have this S inverse. So this should feel a lot like the normal distribution from multivariate linear regression. All right, so S is our spread matrix. Typically, this is going to be a covariance matrix, but it doesn't necessarily have to be. We're being a little bit more general than that. But practically speaking, almost all situations, S is going to be a covariance matrix. All right, well, if we remember that the generalized likelihood ratio can be written as a matrix times the log of the compositions that with a difference. And so here, if I represent this as psi times log of z, I can rewrite this entire equation in this format here. All right, and so this is being replaced by psi times natural log of z. This is replaced of psi times natural log of z prime. And you'll notice I've got a transpose here. Well, taking the transpose reverses the orders. So what I would have here, if I did the conversion, I would have, or this would be psi log z minus psi log z, then do a subtraction. And so now when I take the transpose, remember transpose changes the orders. And now we have the log z and log z prime on the left, and we have the transpose of psi on the right connecting to this part. Over here, it's exactly the same story. And so we have, now we're not transposing. So this is psi times log z. This is psi times log z prime. We'll factor out the psi and we get exactly this. And so then we have one clean formula, and so it's more nailed down for us. All right, so remember that the z and z prime are compositions. We want the distance between our compositions. S is a spread matrix with respect to whatever transform we're going to be using. It's important that S has to be in relation to the transform that we choose for this. And then psi is the matrix of the log ratio transform. Now, the Atchison Mahalanobis distance can be computed using a log ratio transformation as long as the spread form of S is transformed accordingly. So it doesn't really matter which transform we use as long as we just make sure that all the P's and Q's are correct. The distance computed will not change from log ratio transform. That's important. So if I choose a different transform, the distance between observations is going to be the same as long as I mind my P's and Q's, cross my T's, dot my I's. And this distance is affine equivalent because I can change the transformation and it doesn't change the distance between observations. Now, the distance metric is a Euclidean metric. So what that means to non-mathematicians, this means that it has an inner product. So I can take the dot product with it. And so the dot product of two compositions with respect to a certain spread matrix is going to be the generalized log ratio transform of the whichever one we choose for our project, transpose times the inverse of the spread matrix times the generalized log ratio transformation of Z prime. And so then just going through the same process we did up above, we can see that this is another presentation of that dot product. And so here we have the log of the composition. Here we have the log of the composition. That should be a prime. I fixed that, but I forgot to run the R markdown file. There should be a prime right here on this guy. And then we have psi transpose, we have psi, and then we have the inverse of our spread matrix. Now, our spread matrix is going to be symmetric. That has a lot of implications in the range of linear algebra, or not the least of which is that it's going to be positive definite. That means that if I take vector on the left times the matrix times the same vector on the right, I have to get a non-negative value. It's semi-positive definite, and also it has non-negative eigenvalues. All right, so it could be 0 if it's a low rank. But in practice, in real life data situations, we almost never have 0 for eigenvalues. And then we also have a Chomsky decomposition. All right, so the Chomsky decomposition is just that S can be presented as R times R transpose. Okay, well, how do we get that? Well, remember that S is symmetric, which means that it's normal, which in all normal square matrices can be unitarily diagonalized. Okay, so what that means is that S can be represented as a unitary matrix times a diagonal matrix, in this case with non-negative entries, times the inverse of the unitary matrix, which is Q transpose. Okay, so or the adjoint, depending if we have complex values. All right, so when I take this, knowing that all of the entries on my diagonal matrix are 0 or positive, I know that this diagonal matrix could be factored into the product of the square roots of the diagonal. So I take the square root of the diagonal, put on the left, square root of the diagonal on the right, and that is equivalent to that diagonal matrix. And so now I know what this R is. I know that it is the unitary matrix I have here times the diagonal matrix I have here, except I take the square root along the diagonal. All right, well, why do we care? That's a very good question. I'm glad you asked. This matrix R allows us to simplify the computations of what's going on. We can use it to spherify the geometry of what's going on. We can compute the distances in inner products by using either a conventional Euclidean distance, that's when we compute the distances, or we can use a dot product for the inner products. And so when I'm computing the distance, because of this representation that I have with the Cholesky decomposition, I can compute distances as a Euclidean distance to make things easier computationally, easier to interpret, easier to understand. And for the inner products, I can use a dot product to accomplish this. The spherified coefficients of the composition are just going to be R inverse times the generalized log ratio transform of Z, which can be rewritten as the diagonal matrix with the square roots, but reciprocal on the entry. So here, for us to have this, we have to have non-negative, we have to have non-zero eigenvalues. So we have to have full rank for S. But that's really not a high bar to reach in real life data. Here we have really the inverse of our unitary matrix. And here is the author of the textbook puts down transpose. If we have complex numbers, we would have the adjoint instead of the transpose. And here's the generalized likelihood ratio of Z. So a random composition is said to have an additive logistic normal distribution that is the normal distribution on a simplex, if its vector of log ratio transform scores has a multivariate normal distribution. So what we're saying here is if I can do a log ratio transformation on my composition and get multivariate normal, then I have an additive logistic normal distribution. And we would like to have that so that we can run our analysis and use the full power of the normal distribution. And now this is true for any log ratio transform. So for added log ratio transform, centered log ratio transform, isometric log ratio transform, or even pairwise log ratio transform. All right, so the probability density function for this normal random composition can be written in this format. So this is going to look a lot like multivariate normal, but we're going to have a little bit of a twist in here. All right, so just like in multivariate log normal, got 1 up top. I have a square root here. I have a 2 pi. So this is going to be 2 pi inside a square root, along with a power of d minus 1, because when I do my compositions, I'll have my last entry as my reference level. So I know the sum of all the values have to be 1, 100, 1 million, whatever it is appropriate for our project. Because of that, if I know all but one value, from a math point of view, I know that last value. There's no randomness to it. And so it's d minus 1 off of this. Now here we have our spread matrix. Now we're going to take the determinant and take it to the power of d minus 1. So notice that here we're going to have a d by d matrix determinant to the exponent of d minus 1. Now up here I've got that distance. This is going to act like x minus mu over sigma for the purpose of comparing to univariate normal. And so the distance here is squared. This is like x minus mu over sigma in the place of the distances to connect back to univariates. Now something about this. We're talking about spatial statistics. The whole point of this textbook, whole point of this video series is about spatial statistics. I haven't talked about spatial statistics at all. It works out that spatial dependence really makes the normality checks useless because I've got the spatial component and the univariate values also going on, the multivariate of the multivariate distribution of the log ratio transformations, in addition to the spatial component. And really, I can't decouple this. And so really, the normality checks really are not as informative and useful as they are in other lanes, but it's expected. All over the place in statistics, we check normality, and you know what? I probably should check it. Even if it doesn't make sense because of spatial dependence, I still should do it just to understand what's going on in a more complete manner. So it's customary for us to do checks of normality in non-spatial statistics. Something that we do when we do spatial statistics, I'll do like my univariate analysis or the multivariate analysis independent of my spatial statistics. I'll look at my spatial data separate of my measurements before I put them together. And this way I'm baby stepping to understand my data as well as I can to get the best results possible. I want to understand bit by bit so I get a clear picture of what's happening. And so here, we're still going to do this check, but I have to keep in the back of my mind, no matter what I decide, normally distributed or not, I don't have the full story. I can't really accept or reject any hypotheses. Okay, so the composition package gives us this function for normal goodness of fit tests. And this is using an energy test for multivariate normal. And so we can see that it's definitely not multivariate normally distributed. Here I'm doing the isometric log ratio transform. This is what the textbook author referred to. And so here, if I do univariate distribution checks, well, here, this looks pretty skewed. And these frankly look, too peaked to be normal to me in my eyes. But, so this, if I have univariate, not normal, then I have to have multivariate. It can't be normal overall. So I would conclude not normally distributed. But when we take into consideration the spatial aspect, it may actually work that way to be normally distributed when I start considering space. And so I'm not done with the hypotheses yet. All right, so diagrams for visually checking normality of a composition can be attained based off of pairwise log ratio plots. Each panel represents a conventional graphical check of normality. For instance, we could do a QQ plot. And so this is actually what we get when we do QQ norm on an Etchison composition object. All right, so in the plots I'm going to show you in a moment, it's not unreasonable to say that aluminum 2, oxygen 3 versus the residuals would be normally distributed. But when we look at iron versus residuals, we would say, hey, this absolutely is not normally distributed. And so the QQ plot of the iron versus residuals shows the presence of a very small group of perhaps 10 samples that are radically different from the other samples. This small group of samples may be polluting the representation. It may be that I actually want to exclude these. Maybe these are a subpopulation I need to study further before I go and start running before I reach my conclusions. All right, so aluminum and the residuals. All right, so we do have a little bit of deviation. The authors of the textbook feel this is okay. I actually don't like this bend right here. I would be leaning away from normally distributed if I wasn't going over a textbook, but the textbook author is okay with it. So, all right. What now for iron and the residuals, you can see that here we have drastically, wildly different. So this is definitely not normally distributed. No questions about it. Now, if I go through and I check this out, I'll notice that, hey, that looks like a reflection of this if I was to rotate it 180 degrees. This, if I rotate it 180 degrees, I get that picture. Here in the corners, 180 degrees off of each other, 180 degrees. And this is not a coincidence. The reason for this is that when I do that log ratio transformation, I'm taking the logarithm of the ratio. Well, the logarithm of a fraction is equal to the negative logarithm of the reciprocal. And because of that, I'm going to have this reflection aspect on the visualizations every single time. And so I'm seeing the same thing twice. And hopefully, like, we really catch it well when we go through this. Now, if I had a very large data set, I could use that to cut my work in half to do fewer plots and fewer calculations. All right, so now we could also do log ratio transformations with other tools. And so how I chose to do this, I was thinking about this, like, so the textbook shows that for me to be able to use normally distributed, I have to have the log of the ratios. Well, when I have the ratios, I've got d times d minus 1 possible choices. Now that is when I'm counting like numerator over denominator different than its reciprocal. All right, so I was thinking about how would I do this to be in R to go through and work this out. All right, so what I chose to do to be able to put my data into long format, a tidy format. So think about the original version of a composition data set. Each observation, so for us, each location where a sample was taken is a row, then I have fields all the way across. Well, if I want the log ratio transformation, then I need to take every possible pair in a row with distinct different field values. So like Al2 oxygen 3 with iron, and then I want to take those values and put them in their own line in long format. And so how I was trying to think of the fastest way to do this, most efficient, and I think this is pretty good. Let me know if you can come up with a faster way to do this, but I'm just going to go through, I'm going to grab every possible pair and grab just those two columns and put those into long formats. And then I'm going to stack all of them on top of each other. And then once I have them stacked on top of each other, I can go through and compute my ratio. And once I have the ratio, I can compute the logarithm of the ratio. And then once I have it in this format, I can do anything and everything in the tidyverse that I want to do on the log ratio transform data, because now I have exactly those. Now here, I always like to put color in my plots. And so I'm going to set it up so that I have the bins. I'm going to bin into 3 groups so that each color is 1/3 of the total data in the entire data set. And here are, now one thing I did was I looked at the raw averages of each of the fields, and that's in the original data, not the residuals. And I ordered from most to least. And so by doing this, this helps me analyze what's going on, because I know that iron has a higher proportion in my samples than LOI, which has more than SiO2, which has more than aluminum 2O3, which has more than Mn, more than P, more than Cl, and more than S. And then composition residuals, the authors use those as the reference point. So I left that at the very end. All right, so when in the plots I'm going to show you in a moment, iron and composition residuals appear to be the farthest from normally distributed, while Al2O3 and LOI appear the closest to normally distributed. Now, something that's going to happen, I'm going to do the Shapiro-Wilk test. Shapiro-Wilk test for large samples is practically guaranteed to reject the null hypothesis. But if I see a larger p-value compared to others, I know that the distribution of that is going to be closer to normal. Smaller p-value will be farther from normally distributed. And so this gives me a way of just trying of spotting what's going on. And so in this data set, iron and composition residuals are the farthest from normally distributed. Al2O3 and LOI are the closest to normally distributed. And everything in the middle is kind of like along a spectrum there. All right, and one thing that you'll notice is that once again, the numerator denominator distributions are going to be very similar to their reciprocals, logarithms of the reciprocals, just because of the logarithm properties with reciprocals and negative values. And so when I go through, I'm doing the Shapiro-Wilk test. And here is where I have the smallest p-value. So these are this pair is the farthest from normally distributed. And you'll notice I have exactly the same pair, but different numerator denominator relationship. And so as I go through, you'll notice that pairs always have the same p-values. That's not a mistake. It's not a coincidence. That's just by how things are set up. And so if we scroll down, we see that Al2O3 and LOI are the least far from normally distributed. Now, the p-value from a hypothesis testing point of view at 0.05, I would say it's not normally distributed, but let's look at the plots in a moment, and I'll let you decide if it's close enough. All right, so here I went through, I only plotted the 4 that are relevant to what I was discussing. And so here we have, so here's Fe, iron and composition residuals. And we can see that, we saw this before, this is pretty far off from normally distributed. If I switch the order, where is it? Oh, here it is. We see that we have a reflection, 180-degree rotation of the composition residuals. And now, if I want to look at LOI and aluminum 2O3, we see that this is pretty close. There's a little bit of bumpage there that I don't like, but honestly, I feel okay with this one. To my eyes, this is okay. If I switch to the other direction, I see I have the same thing, but rotated 180 degrees. Now, when we look at the histograms, iron and the residuals, we see that that is definitely not normally distributed. That is not normal. And we see the same plot here. Then the title got a little bit clipped, but if I was presenting to stakeholders, I would take the time to make an adjustment, but I think it's okay here. Now, LOI with AL203, we can see that, it's not too far off from normally distributed. We have some weird peaks going on here, but I would, if this was something for like a NOVA, I would go ahead and just accept it as normally distributed for the purpose of testing. And let's see, where is it? Oh, and here's the other version. So here, AL203 is the numerator, LOI is the denominator. Those are switched, the reciprocal, and we can see that we have the same shape of the blue and the red, and then the green is just a reflection of each other. All right, so punchline of all this. If a log ratio transform of my data results in normally distributed when I'm working with composition data, I'm going to take advantage of that to do statistics and get an analysis. After I get that analysis, I will convert back to the original version of composition to reach my conclusions. I hope you enjoyed the video. That's all I've got for you. Life is short. Do math.